like this. So our wave port is placed at this position, whereas our region is extending up to this point. So what we can do, we can go to region, select it here, then double click, and in minus Z we put 0. Okay, so now it is touching there. So again go to simulation and validate the design. So that error has been resolved. Now one more error, that is analysis. We need to define a solution setup. I said that we are ready for the simulation, but at what frequency we are going to uh, simulate. As for that, here we select this analysis and right click on this and add a setup. We are going to use the advanced setup, not the auto setup. In advanced setup, we have three options. We have an adaptive solution at a single frequency or a broadband frequency. I am giving a broadband frequency and I want to design the antenna at 2.4 gigahertz. So I am giving 2 gigahertz to 3 gigahertz. Okay. And then these are the number of passes that I am going to explain you. So if you are able to see, here there is a circle. Let us start with a simple square. So what happens in simulations? We solve the Maxwell's equations, and those Maxwell equations we are not solving at infinite amount of time. We are selecting certain points on which we are going to solve those problems. For example, right now in this circle square we see 1, 2, 3, 4. These 4 points we are going to select this equation. Okay, then that will give very ambiguous results, because what happens in between these points we are wrong. Then what happens, we can increase the number of points by drawing two more lines like this. Now we have 1 2 3 1 2 3, total 9 points to calculate the fields. Again, if we refine, that means we increase the number of points. So like this. So here we are able to see more number of points. Again refine. So like this, we can increase the number of points. And let us reset this. Now you can see that there is a convergence flaw. At first point, when I increase the number of cells, number of mesh, it it has nothing there. But again, when I increase, it is displaying a graph. Okay, so between two consecutive points, it is displaying the change in the uh, results. So that results that can be identified as the S parameters or the electromagnetic energy inside the structure. So as we increase the number of refinements, you can see that that difference is decreasing. Okay. So that is the principle that is used inside this HFSS. So it will be calculating the parameters at the center frequency, that will be around 2.4 or 2.5 gigahertz. And it is targeting that between two consecutive passes, we have a maximum of 0.02 dB variation in the S parameters, and maximum number of passes we are setting as 6 passes. Okay. For higher accuracy, you can increase the number of passes, and we click on OK. Then once we click on the that has selected a wide frequency range, so we need to define a sweep there, that from what frequency range we are going. So the start frequency we are giving as 2 gigahertz and frequency is 3 gigahertz, and the default number of points are 401. That will be very high, so we change it as 400 and 101. Okay, now this sweep has three different types. So discrete sweep, interpolation, and fast. So we are, for this simulation we are going to use the fast sweep. We if we want better accuracy, you can go for discrete or interpolation. but that depends on your hardware, how much RAM do you have and how much time it will take. So we are selecting the fast switch and we are saving the 3D fields, and there is an option to save only the radiation field instead of the complete electric and magnetic fields. That will reduce the size of the your file. So right now we are selecting all the fields. Click OK, and then now when we validate, everything is perfect. And it is one more thing is there, that it is radiation. So click on this radiation, right click, insert far field, and give an infinite sphere in which phi is varying -80 to 180, theta is varying 0 to or 30 to 180, and in steps of 2, that will be very in steps of 10 degrees. Okay, so it will create a sphere around the model, and at the points of that sphere, we will be calculating the electric electromagnetic field, and from that we will be calculating the gain and other parameters. So now everything is set up. Now click on the analyze call. So for that, I need to save this and save this file as project 2. Now it is running, and at the same point you can click on this result, and you can click on the solution data. Okay, in solution data there is a profile and convergence. So we have maximum number of 6 passes, and we are setting the maximum magnitude delta, that is 0.0602. So what happens that suppose after 2 or 3 passes, the variation in the S parameter is below this target, then the setup will stop. So the first pass is completed, and there is no make delta S because it is the first pass. Now the second pass is completed, the magnitude difference is 0.08, and so still the program is not converged. In third pass, the program is about to converge, but no. So 3 passes have completed. Let's see in fourth pass. In fourth pass, the outcome is like this. So the setup has converged. So we can also see the plot like this. So this was the limit, and we have reached this. After 4 passes, we have stopped because the delta S is less than 0.002, zero point 0. Okay. Now, if you see the profile here, you see that when the simulation started, the initial meshing was 33 mm. It was consuming only 33 megabytes of your RAM. In the last pass, after 4 passes, you see the memory is 600 megabytes. That means 10 times of the first pass. So if you want higher accuracy and you set this up to very high value, this target value is very low value, then the number of passes will increase, and you will also increase the number of passes. Then at certain point, it is possible that your simulation setup is not converged, but your system has gone out of RAM. So be careful about the size of your data. Okay. Then now the simulation, it is showing that normal completion of simulation. Okay, so now we have completed this simulation, but where are the results? So in results, there is nothing. So actually we need to create the reports. So right click here and create a model solution data report, create a rectangular plot. So in that we can select the S parameter, and we have only one port, so we are only able to see S11. Then there are other parameters like we want to display S11 in dB, or we want to normalize them to 10 dB or 20 dB. So let's go with the default setup. Okay. So now, as we have not calculated the exact dimension, so it is giving us simulation up to this point. Okay. Now, again, right click here and select a rectangular plot. This time we are going to use Z11, and we are not going to use dB parameters. We are going to use real and imaginary parts. Okay, so real and imaginary. So you can see uh, we can overlap, we can either modify this report and real and imaginary. We can add the traces, and in those traces, we can give it as white. So from here, we can see S11. From here, we can see real part of Z11 and imaginary part of Z1. So you can see that the S parameter dip is here. The real part of the impedance is maximum at this point, and the imaginary part of the impedance is not touching the zero. So that means we need to optimize our design to so that the imaginary part is maximum, or it is matching to 50 ohm, and the real part is 50 ohm, imaginary part is 0, and we have S11 dip there. Okay, so I have created some simulations earlier, and let us save this first. Now let us save this design, and let me show you the designs that I have stored earlier. Open, click open, and this is the design that I have created earlier. So we are using a coaxial feeding. In coaxial feeding, these parameters are like this. So I have optimized the design. That means I have optimized the parameters of the design, and you can see the Z parameter. The real part is about 47 ohm, and at that point we have very less value of this imaginary part. So from this project, from these results, what we can conclude that when we are going to define the frequency, we can right click here and add some markers. Let us add a Y marker, and that Y marker is on, we are placing it on -10. So in the S11, the parameter is uh, the S parameter is below 10 dB at 2.694 gigahertz to 2.738. This is your impedance bandwidth, and you can see in this range the impedance is below 50 dB, and the imaginary part that is like this. So this S parameter is a combination depending on the input results. So you might see that the imaginary part is not even touching the zero, but since the real part is very close to 50 ohm, therefore we are getting this matching. Okay, so in order to improve the matching, what you can do, you can change the position of the feeding. So we have given the position as a variable. Remove this and select fit all. So this is the position. So we can shift this without changing the physical. Like if I click here and make some changes and then click OK, then my current results will be deleted. Okay, so that is why we have already taken care that we can change the dimension without going to this window. So what we can do, we can select this, click at this position, we select this design, then all the parameters that are that we have defined, or the variables that we have defined, we can identify those variables. Okay. Now this de-embedding, this is when I click here and see the design properties. So all the parameters that all the variables that we have declared, all these variables are of type design type. But this LD embed, that is a post processing variable. So if we change any of these parameters, that will change the physical structure, and all results will be discarded. But if I change this LD embedding, that is a post-processing variable that will not discard your results. Okay. And why do we use this? Let me show you. For example, this is a patch antenna that is fed by insect feeding, and in this I have applied this de-embedding, and okay. So here you can see. I think I have to re-verify that. Okay. Tomorrow I will give that demonstration. So here we have selected this S parameter and we have selected the Z parameters. And now we need to see the field report. So you select here, create a field report here as a rectangular flow, and right click, create a, create a far field report, because the antenna parameters like gain, efficiency, those are parameters at the far field. So we select the create a far field report, then click on the variable, then we click gain total, and the unit of that will be dB. Now, uh, uh, from which simulation we are going to extract get the solution. So we have a setup, that is last adaptive setup, and we have a sweep. Last adaptive setup, when we are select that is when we are selecting the mesh size. Then we once the mesh size is completed, this that was done on a single frequency, that was 2.5 gigahertz as center frequency. Then we have a sweep. So first, let us draw this at the last adaptive. So in last adaptive, then we have this so many figures, so many diagrams, and we are seeing the result at frequency 2.5 gigahertz, phase angle minus 180, minus 170, all those phases. All those for all those cuts, we are able to see the results here. Then I want to see the results at this. How our antenna is radiating at this point, 2.7 gigahertz. I want to see the result at that point. So if I go to this report and click on families, now I want to select the frequency. I'm not able to select any frequency because this last adaptive has only one frequency. So, let us select this sweep, and then I will be able to change the frequency. Okay. So now we can change the frequency, then apply. So here we are able to see that the maximum gain is about 2.5 dB, and this is showing a different result. Now right click here, and another thing is create antenna parameters. So antenna parameters will not show this many graph. It will give us antenna parameters like the peak directivity, peak gain, peak radiation, realized gain. These are the things that we can identify. So let us draw this peak gain and peak realized gain in dB, and we are going to use the sweep and click next. So what will happen that if you can imagine the 3D sphere. In the 3D sphere, we have pi minus 180 minus 170, these 36 parameters, and for theta there are 18. So for all those points, it is calculating the gain and identifying the maximum out of those points, and that will be displayed here. And in addition to that, if you want to create a far field report and a 3D polar flow, you can also draw that. Okay, so let us wait for this to complete. think I have made too many points. So, whenever you are saving the fields and you want to draw a frequency versus gain chart, then you need to make sure that there are sufficient points for a smooth graph, but it does not exceed, because for every frequency you will have to, the software will have calculate. So if you see here, currently it is calculating for 2.44 gigahertz, and it has to calculate up to 3 gigahertz. Okay, so at each frequency point it is calculating and it is moving in that same way. Now, as we have all set only 101 points, that at that time we are getting this many. What let if we assume if we have taken 1000 elements, then how much time it will take? So that all depends on your requirement, how you want to analyze the system. Let us wait for 5 minutes. Now, if we close, then we are able to see that this is the peak realized gain, and this peak realized gain, and just copy this, copy data. Okay. So the peak realized gain at this point is around 2 dB, and you see the peak gain. Peak gain is way better than the realized gain. So whenever you are reporting your results for the gain, you have to mention the peak realized gain, because the peak gain does not consider the effects of losses, and that does not consider the effect of your efficiency. So this realized gain, this is the actual gain that you will be able to measure in your setups, and uh, this is the result. And now let us go far field report and create a 3D polar plot. And we are going to use the sweep and select the frequency as 2.7. CAC department हमारे okay. So now you see were plotting gain, and the total gain we were plotting. We have not selected this, so let us apply this dB. When we apply trace, so this is the kind of so let us rotate this. This is the radiation pattern in 3D, and we can also create radiation pattern in field results. We can also create the same radiation pattern in 2D and select the x-axis. In rectangular plot, we can use select the sweep and 2.7 gigahertz. And for we will be selecting it for phi equal to 0 and phi equal to 90. In these two planes, we are going to draw this. So this is how the field is moving. We can also create when we right click, we create and we can create radiation pattern that we used to see in the books. Okay. So now, right now, we are not able to. We are only able to see the half part of this radiation pattern because we in the definition of our radiation pattern, we have selected theta from 0 to 180. If we select it from minus 180 to 180, then we will have this will update from the results and we are able to see this. Okay. And if you want to draw here the uh, you want to draw the co and cross polarization, you can do that. Okay. So here we are able to see that this is giving a highly linear polarization because the cross polarization levels are way beyond this. It is 2 dB and this one is minus 38. So it is way beyond the required polarization, cross polarization level. So our antenna is giving highly resonant. So what we need to do now, we need to optimize the dimensions of this patch. So we need to optimize this WP and LP, and we need to optimize XP. These three we have to change and analyze the results. And we need to make sure that the S parameter is has a is below 10 dB at 2.4 gigahertz. The peak is at 2.4 gigahertz. Then we can say that we have designed the antenna. I think we have around 540. Any questions? If anybody have any question so far,
Participants, you can please ask the questions if you have any query.
okay. Okay, Swati, you can please collect the query. I am giving coming in 5 minutes.
Okay, okay, sir.
Okay. Okay. So Afrin is asking, how can we identify the polarization from radiation pattern? How much time? Okay. So the polarization that depends on the shape and alignment of your antenna. And right now we have only created a simple microstrip patch antenna that is a linear polarization. From the here from this graph, if you see, there are different type of gains. We have a total gain, then we have phi, theta, x, gain x, y, z. So if currently we have aligned our antenna in x and y plane, so it is z polarized. Okay, and if our antenna was a circular polarization, then we might have seen the LFCP or RSCP radiation. And with that, what we can do, we can check for the Excel ratio. Excel ratio gives us, if the value of Excel ratio is below 3 dB, then we can say that our antenna is circular polarized. For linear polarized, it is highly recommended to have very high Excel ratio. If it is more than 40 dB, that is highly highly linear polarized. If it is above 20 dB, then it is linear polarized. In between, we have elliptical polarization between 3 dB to 10 dB. That is a elliptical polarization. So we can draw the from this plot where we have plotted this antenna parameters. At this point, we might have plotted this Excel ratio also. Okay, right. If we create a report and antenna parameters report, let us say this is your direction. So you can see that the peak rate direction of radiation is theta 0 and phi 0. So we click here and click on the far field, create a report in uh, give me 5 minutes. Okay, so we go to the report and select Excel ratio, then plot the Excel ratio in dB. Now select the sweep and we are going to plot this Excel ratio versus frequency plot here. So we select in the primary sweep as frequency, then go to families and select theta is 0, phi is 0. Why we are selecting this 0? Because the direction of maximum radiation is 0. From the 3D plot, we see the direction of maximum radiation is 0. So we are selecting it, we are calculating the Excel ratio in 0, 0 direction. And with respect to frequency, we are calculating. Then create a new report. So you see the Excel ratio is above 37 dB at all frequency points. That means it is highly linear polarization. Then when we are plotting the co and cross polarization, so that is, we can also identify from there that we have the core polarization and cross polarization, they have very huge separation gap. Okay, and so we are able to say that the antenna is linearly polarized from Excel ratio. If it was less than 3 dB, then we could say that it is a linearly polarized. At that point, we have to calculate the LSCP and RSCP plot. Then we identify whether it is a left-handed circular polarized or right-handed circular polarized. Okay, and I hope Afrin, I got it, your queries resolved. Dr. Ramesh, how much time required to understand this HFSS tool? That all depends on the time and practice you give. I think if you give 1 hour daily, then within 6 to 7 months, you might be able to have a better understanding. But you need to practice on different tools. It is not like you are just doing the same thing again and again. And is it possible to design MIMO antenna? Yes, we can. We will be working on MIMO antenna in this software. In next sessions, we will be working. Can we design any type of antenna? Yes, most of we can design. If you can create a model of that antenna, you can simulate it inside the software, inside XFSS. Okay, it all depends on your creativity. For example, I have created this simple microstrip patch antenna with simple rectangles, and I did selected a particular methodology. You can create your own methodology. What is antenna we can design it? Yes, for millimeter waves, it is possible, and we will also design a antenna for SIW at 28 gigahertz. We will be designing an antenna in next sessions. Is it better than CST or both are same? Okay, so that is a very tricky question because CST works on a different principle and HFS work on different principle. Both of these softwares are 3D simulation softwares, and both are fully 3D, and at CST works on finite time domain difference, whereas HFS work on finite element method. So both the methods are different for analysis of the problem, but the results they are very close to each other. Okay, so if you have the right simulation, then both of your results will match. A maximum 5% of variation will be there. If there is more than that, the difference is more than 5%, then you should analyze, you might have done something wrong in any of the design. Okay, for biocompatibility, what we can do, we can develop some models, and we need to determine the properties of bio those models. For example, we can have a vortex model of the head, and we can analyze the antenna impact, and we determine the SAR values using this. Okay, but that will require a lot of memory in terms of RAM and size. Okay, so tomorrow I will also describe you a little bit more about how this meshing is impacting. So if you see in this results, the solution report, I have already shown you the profile. In the first pass, the memory was around 29, 100, 200 MB. That was the maximum. And in the last, we are going up to 600. So the size of your model and the frequency at which you are operating, that affects your calculation size. Okay, but definitely you can do this, and I think this student version limits you with the calculation. So biocompatible, you can have a academic license in your institute, and in that you can calculate the SAR, etc. Any more questions?
Thank you very much, sir. Sir, undoubtedly, this session was very much informative, and surely our participants are able to understand the HFSS from the scratch. And if the participants have any more query, you can drop in the chat box. We can ask tomorrow also. Thank you very much, sir.
Okay, thank you very much, ma'am. And that was a great session. That was very nice experience with such in, uh, intuitive students. I will be happy to share tomorrow also. And if you have any, okay, what is the cost of HFSS academic license? You might need to contact the vendors. I can give you the vendors number tomorrow. Okay. Okay. Uh,
Thank you, sir.
okay.
We
Thank you very
can, I
much.
think,
So
end today's session.
let's hope we see you tomorrow. Okay. Uh,
Okay, sir.
should I close now?
Yes, sir. Yes. Dear participants, tomorrow the session is going to start from 9:30. You are required to please join at least half an hour before. If you have any issue, yes, Rahul sir, yes, if you have canvas issue also, we'll work on that. And soon we will solve your canvas issue. Thank you very much, sir. Thank you.